At this point, I kind of feel like we've done enough average rate of change examples, both algebraic and geometric, that I probably don't even need to do this example, but I'm going to do it anyways, just in case people want one more problem to practice off of. So the idea here is, in the previous videos, I either represented the function geometrically with its graph, or I represented the function algebraically with its equation. In this example, I do both. So this equation corresponds with a machine whose graph looks as pictured. So what we're asked to do is find the average rate of change from 1 to 5 of this function, and we can answer that question either geometrically or algebraically. If you're going to do it geometrically, what you'd want to do is locate the points where x equals 1 and where x equals 5 on the graph. So here's where x equals 1, this is the corresponding point on the graph, and here's where x equals 5 with this point corresponding on the graph. This point has an x-coordinate of 1 and a y-coordinate of -2. This point has an x-coordinate of 5 and a y-coordinate of 6. To figure out the average rate of change, all we have to do is figure out the slope of the secant line, which is this line pictured in black, and then we'll have the answer. You can do this two ways. You can just kind of visually figure out the slope. It looks like it goes up 2 units every time it goes right 1 unit, therefore the slope must be equal to 2. Or you can calculate the slope using the average rate of change formula, where we take the difference in the two outputs, the two y-coordinates, f of x2 and f of x1, and divide that by the difference in the two x-coordinates, x2 and x1. So using this point as my 1s, x1 would be equal to 1, and f of x1 would be equal to -2. And then if these points are my 2s, then x2 is equal to 5, so in the denominator I get 5 minus 1. And f of x2 would be equal to 6, so in the numerator I have 6 minus -2. Let's see, 6 minus -2 is the same as 6 plus 2, which is 8, and 5 minus 1 is 4, and 8 divided by 4 is 2, the same slope that we came up with when we just visually inspected the slope of the secant line that's pictured. But maybe you don't want to use the graph. Maybe you instead just want to use this equation right here. No problem. We'll still let x1 be equal to 1 and x2 be equal to 5, and all we'll have to figure out is what is f of x1, which we'll figure out not by looking at this y-coordinate, but instead by putting 1 into this machine. Let's see, 1 squared minus 4 times 1 plus 1. 1 squared is 1, minus 4 gives me -3 plus 1. I guess that gives me -2. Oh yeah, sure enough, this -2 that I see here, I could have calculated algebraically this way. And for f of x2, all I got to do is put x2, which is the number 5, as indicated here, into this machine. F of 5. F of 5 would be 5 squared minus 4 times 5 plus 1, copying this equation, changing all the x's into 5's. So let's see, 5 squared is 25, minus 4 times 5 is 20, plus 1. 25 minus 20 sounds like 5, plus 1 more. I guess I have 6. Oh, right, this 6 that I see right here. I can now take these 4 values, the two x-coordinates and the two corresponding f of x coordinates, and put those into my average rate of change formula. In the numerator, I would have 6 minus -2, and in the denominator, I would have 5 minus +1. Same values that I got when I did this thing geometrically.